This video is a continuation of the last video where we're going to talk about radial acceleration. I'm going to give you an equation without proof right now, and then we'll make another video where we do prove it, and then I have an exercise for us to do also. But let's start with the magic equation for now. We'll prove it in a future video. But here's what we need to know is the radial acceleration that's needed to turn an object. Needed to turn an object is two things. Directly proportional to the square of the object's speed, of the object, in other words, that radial acceleration is proportional to speed squared. That maybe it's not surprising that it's proportional to the speed in some way because, as you know from your driving experience or other turning experience, if you're going faster, it's harder to make a sharper turn. And then the other factor that matters is that it's inversely proportional to the radius of the turn, or the circle. So the other thing is that radial acceleration is proportional to 1 over the radius. And that might make some sense too. A smaller radius is going to need more acceleration to turn. It's going to be harder to do that one also because it's a tighter turn. As an equation then, what we get is the radial acceleration is proportional to speed squared over r. And if we look at the unit analysis for this, we get that speed squared has units of meters squared per second squared over units of meters for a radius, and one of that meters in the denominator cancels with one of the 2 meters in the numerator, and what we're left with is units of meters per second squared. And so this already has acceleration units, which is promising. And it turns out, for reasons we will see in a future video, that we do not need a constant of proportionality here. In fact, the radial acceleration is equal to v squared over r. So that is the, you're going to accept that without proof right now. And then what does that look like in the example from the last video where we had 3 forces acting on an object that was turning? And we found that the sum of the forces was adding the 2 forces in the inward direction, then subtracting off the force in the outward direction. Well, what does that look like now? Is that we can apply Newton's second law now. So we can apply Newton's second law with this equation for acceleration. And so Newton's second law is that the sum of the forces in the radial direction is equal to m times the acceleration in the radial direction. And then for our example, what that looks like is F1 plus F2 minus F3 is equal to the mass of the object times the object's speed squared over the radius of the circle. I'll use the highlighter here to emphasize that this term on the right, all of that is the sum of the forces in the radial direction. And grabbing a different color highlighter, this whole v squared over r business, that's the radial acceleration. So those are the same. So that's how we would apply Newton's second law in general to an object that's moving in a circle. You add up the forces in minus out, and then we use this special acceleration equation that only applies when you're talking about a radial acceleration that's turning an object, not a tangential acceleration that would be making the object faster or slower.